Alright everybody, welcome back to Momentum. Today we are going to be talking about explosions. So explosions are like the opposite of perfectly inelastic collisions. An object is originally together post-explosion or post-collision, whatever, and moves separately after an explosion. Okay, so before an explosion, you could think of a bomb or grenade. It's all in one piece. After the explosion, it gets fragmented to different pieces. In this chapter, we're primarily just going to be talking about two other pieces, maybe three pieces at one point, but for the most part, we're just going to be doing two. So in this kind of collision, momentum is conserved, meaning the same amount of momentum it has at the beginning is going to be the same amount it has at the end. Okay, after the collision. Kinetic energy is gained within explosion or collision. Okay, so how is it gained? Where does kinetic energy come from? Well, usually with explosions, there are maybe like chemical properties inside of here, and that chemical energy turns into kinetic energy after explosion. Alright, so the momentum before the explosion, all of the mass times the velocity before the explosion is equal to the masses, different masses, and the different velocities combined afterwards. Okay, moving on. Pretty cool video. It says notice how the watermelon explodes and explain how momentum is conserved. You could watch the video, but we can see the watermelon at the beginning is not moving, but afterwards all the different pieces moves in all the different directions, and if you notice that, it all equals 0. But anyway, watch the video, it's pretty cool. Alright, moving on. 1 kilogram firecrackers at rest splits into two pieces. Piece number 1 has a mass of 0.2 kilograms. Piece number 2 moves with a velocity of 12 meters per second to the right. So let's kind of do some things. This one is 0.25 kilograms. And piece number 2 is moving at 12 meters per second. Okay, we'll call this 1 and this one 2. Okay, what is the mass of the second piece? Oh, wait. Firecracker one at rest with splits into two pieces. Piece number 1 has a mass of 0.25 kilograms. Piece number 2 moves with a velocity of 12 meters per second to the right. What is the mass of the second piece? Sorry. So if this is 0.25 kilograms and this is 1 kilogram, that means this one has to be 0.75 kilograms, because kind of like what we learned about in chemistry a long time ago, mass cannot be created or destroyed. Okay, what is the velocity of the first piece? So we should know that to figure this out, we're going to be looking at the momentum equation. Momentum at the beginning equals the momentum at the end. So we know at the very beginning, the 1 kilogram firecracker is at rest. So it's not moving, 0. After it explodes, we have one piece, which is 0.25 kilograms, moves with a certain amount of velocity. I'm going to do V1. We don't know what that is. We're trying to figure that out. The other piece, which is 0.75, moves 12 meters per second to the right. So we have this. So now we could just do some math. 0 is equal to 0.25 plus, 0.25 V1. 0.25 V1 plus 0.75 times 12, and that's 9. So now we can just move things around a little bit. I'm going to put 9 on the other side. Negative 9 is equal to 0.25 V1. And then we could divide both sides by 0.25. And we get V1 is equal to negative 9 divided by 0.25, which is negative 36 meters per second. Okay. So what is the initial and final momentum? So we know at the very beginning, it's at rest, so it's not moving. So at the very beginning, it has 0 momentum. And if we calculate the final, we know after it explodes, we have, I'm going to do momentum final. So for momentum final, we know that that's going to be, we have one piece that's 0.25 going to the left, 36 meters per second. And then we have the second piece, 0.75 kilograms, going to the right, 12 meters per second. We do the calculations and we find out this is also 0. And that should make sense because the momentum is conserved. 0 at the beginning, 0 at the end. Okay, moving on. Conceptual example number 25. A skateboarder is at rest on a skateboard holding a bowling ball. The skateboarder then decides to throw the bowling ball to the right. Which way does the skateboarder move when they do that? So this is an explosion problem. I know it doesn't look like it, but it's at one piece and then it's at two different pieces. So when this gets thrown to the right, in order for momentum to be conserved, that means this guy needs to start moving to the left. And he does so. Okay, moving on. A skateboarder, 55 kilograms, is at rest on a skateboard holding a bowling ball, 7 kilograms. The skateboarder then decides to throw the bowling ball to the right. Which object moves faster? Skateboarder, bowling ball, both move at the same speed. It's impossible to tell. Think about it. So this goes... So this is 7 kilograms, this is 55. So at the very beginning, we should know that the momentum of these two is equal to 0. So after this explosion, we should know that the momentum should also equal 0. So that means that this bowling ball is going to be moving fast, but it's only 7 kilograms. In order for momentum to be conserved, this one that's a lot bigger, this guy that's a lot bigger, 55 kilograms, needs to move to the left, but a lot less in order for momentum to be conserved. Okay, because momentum is mass times velocity. So the bowling ball is going to be moving much faster because it has less mass. All right, moving on. That might have been a little confusing. Listen to it again if you need to. Skateboarder, 55 kilograms, at rest on a skateboard holding a bowling ball, 7 kilograms. The skateboarder then decides to throw the bowling ball to the right. Which object has a larger magnitude of momentum? Okay, so we know at the beginning the momentum is 0 because they're both not moving. This has a certain amount of momentum. I'm going to call it P1 after it's thrown, and this one has a certain amount of momentum after it's thrown, after this bowling ball is thrown, and we want to know which one has more. Well, what we should know is at the very beginning, the momentum is 0. And we should know after the throw, the momentum should still be 0. So that means P1 and P2 should equal the same, but they're just in opposite directions. So their magnitude should be the same. Okay? Moving on. A cannonball on wheels has a mass of 3.5 kilograms with the cannonball and is at rest. Okay, 3.5 kilograms. It shoots out a 0.3 kilogram ball to the right. The cannon recoils backwards 5 meters per second. How fast is the cannonball moving to the right? So this might be a little bit trickier than it seems. So just be ready for that. Okay, so we're going to be looking at the momentum at the beginning before the explosion and the momentum after. So before the explosion, we have this cannon on wheels, 3.5 kilograms. That's not moving before the explosion happens. All right, so it's just 0. Afterwards, we have this cannonball going to the right with the speed we don't know. I'm going to do velocity of cannonball. But then the cannon, this is now, remember, 3.2 kilograms because this cannon no longer has the ball inside of it. And it goes to the left 5 meters per second, so that's negative. So let's simplify this. 0 is equal to 0.3 velocity of cannonball. I'll do CB plus, and then I'm going to put this 3.2 times negative 5, negative 16. Let's bring 16 to the other side. Oops, sorry. 16 is equal to 0.3 velocity of cannonball. Divide both sides by 0.3. And then that should be, velocity of the cannonball should be 53.33 meters per second. Okay, might have been a little confusing, so watch it back if that was. Moving on. Cannon on wheels moving to the right. While it is rolling, it shoots out a cannonball. How will the cannon on wheels be affected? Select all options that are possible. A. The cannon will slow down but keep moving to the right. This could be possible. If it was going fast and then it shoots out, it might start to go slower but keep moving to the right. So A is possible. B, the cannon will speed up to the right. That won't be possible because when this gets shot out, there is going to be a certain amount of recoil. So it can't be B. The cannon will move to the left. That could be possible. Maybe if it was already only going a very slow speed to the right, after it gets shot out, maybe it moves more to the left. So it could be possible the cannon will stop moving. That could also be possible. It might be going a certain speed to the right, but then it gets shot out and then it gets exactly canceled out. So it could also be D. So A, C, or D. Moving on. A spring is compressed between two blocks with unequal masses, M1, M2, held together by a spring as shown above. The objects are initially at rest on a horizontal surface, no friction. The spring is then cut. Which block will move faster after it is cut? Well, since they have the same amount, different amounts of mass, and this one is lighter, that means this one, after it's cut, will have to move faster than this one. So it'll be M1. Alright, I hope that all makes sense. Next time we'll be talking about the last topic, which is short with elastic collision. Thanks for watching, everyone. Bye.